Turn this on. Can you hear me? Can you hear me? Can you hear me? Can you hear me now? Can you hear me now? Can I hear me now? Oh, hey, can you hear me? Can you hear me? Okay. Okay. Yeah.
Oh, look at that. Good evening. Hey, that sounds pretty good. How's the volume back there? Good? Cool. All right. I'm Angela Metler. I'm an administrative assistant in the president's office at South Dakota Mines. Welcome to Steam Cafe. Thank you for coming. It's very nice outside, so I'm glad to see a good turnout tonight for an indoor event. We do Steam Cafe every third Tuesday. The Steam Café is a partnership with South Dakota Public Broadcasting and Haycam Brewing, so we thank them for their support. We thank you for your support as well. At the end of the presentation, we'll do a Q&A. If you have a question, just raise your hand. Dr. Clabo will hopefully call on you at some point.
That's like class.
Yeah, it is. If you are attending online, so we do broadcast on Zoom, which we are currently doing. If you're attending online and you have a question, you can type that into either the chat box or the question box, and we will make sure it gets answered live. So, without further ado, Dr. Darren Clabo.
Thanks, Angela. Well, thanks. Thanks for coming. It's always better to do presentations with beer, right? Yeah, I thought so. So I'm going to talk a little bit about, our outlook for the summer in terms of fires. But I do want to touch back to history. So this is from the old revised codes of the Territory of Dakota from 1877 that actually talk about putting in laws to prohibit burning in the state of South Dakota. So you'll see, being enacted by the Legislative Assembly of the Territory of Dakota, don't start a fire, basically, in the months of September, October, November, December, January, February, March, April, May, or June. So you can have all the fires you want in July and August, but don't do it in the shoulder seasons, fall or spring, and don't do it in the winter months as well. And I actually found this really, really interesting. And even more interesting is that it's a misdemeanor with a sum not more than $1,000 in 1877. That's, I mean, you would, don't do it, right? That's a really steep fine. But yeah, so in South Dakota, we've been really looking at preventing wildfires, at least human-caused wildfires, since the inception of the territory and since the inception of our state in 1889. So my presentation now is called Sparking Awareness. Thanks, Angela. And we're going to take a look at our summer 2026 wildfire outlook. We want to do this outlook so that we can help our fire partners prepare for the overall fire season, and also to help out any efficiencies that we can. We do pre-position resources in terms of the overall national resources, and already yet this year we've actually had a lot of resources pre-positioned in western South Dakota because we've had a ton of fire activity, which has kept everybody really, really busy, and we don't want the Black Hills to look black this year, right? All right, but first, I got to cross over here, but what is fire? We have to talk about what fire is, how fire actually burns across the landscape before we can even approach a wildfire outlook. So what is fire? Well, wildfire is one of many types of exothermic oxidation reactions, okay? So exothermic means heat releasing. Oxidation just means you use oxygen within that chemical reaction. And the chemical reaction down there is what you see. So basically C6H9O4 is cellulose. You could have what, C6H12O6 in your cups? I think that's alcohol. But it's close, right? It's just basically sugars. And so when we take sugars, we combine them with oxygen, we add the heat of pre-ignition, you can actually get combustion. Throughout that combustion process, especially with hydrocarbons like sugars, you're going to get a lot of water vapor that's released, you're going to get a lot of CO2 that's released, and a ton of heat. All right, it's a ton of heat. It is an exothermic reaction, which means it's heat releasing. But the interesting part about fire is it actually starts off endothermic. The reaction actually absorbs heat because you have to heat the substance to the heat of ignition, which for cellulose is around 625 degrees Fahrenheit or something like that. So you got to warm up the stuff, and then the stuff turns to fire, and then you can burn the stuff, right? So what is in wood? Well, wood primarily consists of cellulose, some hemicelluloses, lignins. The first two things, the celluloses are really sugars, glucoses, that type of things. Lignins, kind of the stuff that makes wood fibrous and strong. Extractives are all of the oils and gums and acids and other things that are inside of the wood. If you've ever seen a ponderosa pine tree or an eastern red cedar tree burn, it burns with black smoke. That's the oils that you see, kind of these volatile organic compounds that come off. And so there's some of that in there as well. But the big part about it for me is there's water in there. And water, it's a really important substance, but it's really, really energy intensive to get rid of. Water is the enemy of fire, and that's why we use giant Black Hawk helicopters and porta-tanks to put out fire, right, when we're on big fires. By the way, that's a fire at the Region 23 complex, actually from 2012, about in the same place the South Fork fire, South Fork, right? Yeah, South Fork fire is going on right now. But yeah, if there's less water in your fuel matrix, you actually get more energy released through the process of combustion. So water, as a firefighter, water is your friend, but water can also be your enemy if it's in the soils. And so we were doing a prescribed burn. Do you remember this? We were doing a prescribed burn up Miracox Lake GPA, west of Spearfish, towards the Wyoming border, and this was a May prescribed fire. I think it was May 2nd. And the grass was really dry. If you look in the background behind our tender there, the grass burned really, really well. But the problem with spring fires, especially May fires, is you have a lot of soil moisture in the ground. And so you can get a fire to burn across the grass. It'll burn the grass just fine. But then when you drive a truck that weighs like 30,000 pounds across the land, it'll sink into that. Jim Burke was actually the driver of that truck, and I gave him lots of crap. So let's talk fuels now, and especially fuel availability. So when I talk about fuels from a wildfire perspective, I'm really talking about anything on the landscape. So that can be sticks, grass, pine cones, unfortunately it can be houses, decks, wood piles, things like that as well. So when we're talking about fuel availability, we want to look at that fuel and say, hey, is it available to burn? And so there's a bunch of different things that go along with fuel availability. The biggest one that we focus on is water. How much water is contained within the fuel matrix? If there's too much water, that fuel is not going to be available to burn. Fire will hit that fuel, but basically the moisture in that fuel is going to be too high, and the fire is not going to sustain itself. Fire, by the way, is not spontaneous. You need this heat of ignition, but fire is self-propagating. Fire burns above the temperature of ignition. So as long as there's no water in the fuel, fire will continue burning. But as anybody who's ever had a campfire knows, fire will stop because most of our woods, things that we use on the campfires, do contain a little bit of water in there. The other two things we have to think about is fuel continuity, and we also have to think about is how compact the fuels are. If you think about something that's really fluffy, right, it's going to burn really, really well. So what we call it has a high surface area to volume ratio. Surface area being the surface of the fuel, to volume being how dense that fuel is. If the surface area to volume ratio is really, really high, your fuel's really fluffy. You know, think like cattails, right? Burns really, really, really well. If your surface area to volume ratio is really, really low, that's like a big log. So you're not going to want to start your campfire with a big log, right? It's got a really low surface area to volume ratio. You're going to want to start your campfire with something that has a higher surface area to volume ratio. You can incorporate more heat in the fuel matrix, you can incorporate more oxygen into the fuel matrix, and then conduction, the heat transfer process, works much, much better with those fuels with a high surface area to volume ratio. So these are just things that we have to think about when we approach a wildfire season. All right, so I'm going to get into the weeds a little bit. They're dry weeds, though, so we can burn them. So fuel dryness and fuel moisture. We have to think about things in terms of, are they live fuels or are they dead fuels? So we do break these two things apart. Live fuels are like our herbaceous and our woody fuels. So I have in front of me, for those of you online, you probably can't see it, but this is, I don't know what this is. I'm not a botanist, but this was what I would call shrubbery, right? Shrubbery. This is a live fuel. I pulled this from the hill behind campus today. It has an amount of live fuel moisture to it, and it's growing. At least parts of it are growing, right? And so inside of these twigs that aren't growing, they're pretty snappy. I'm a very tactile person. I like to break things. If it sounds snappy, it's dry, it's going to want to burn. But the side that's living is much more flexible, right? You could tie this into knots because the fuel moisture inside of it is much, much higher. When we talk about fuel moisture, that is literally the percent of moisture that is in this thing. So if I took this twig and I were to go dry it, let's say this twig weighed 110 grams, and I went and dried it in an oven, dried it for 2 days, completely dried it out, and this twig then weighed 100 grams, right? Its fuel moisture would be 10%. Follow? And so living stuff tends to have a much higher fuel moisture content than dead stuff. Living stuff, even in the wintertime, we consider living stuff to have a fuel moisture of about 30%. That's what we could consider cured out and basically dormant for the season. This time of the year, though, the amount of moisture starts to exponentially increase inside of our plants because they're uptaking water from the ground. Well, if there's water in the ground, which there really isn't, but that's a different story. But they will take up some water, and once they get that, they call it full turgor, and that's when they get up to about 300%. By the way, when this gets over about 150% fuel moisture, it will not burn, which makes fire people sad. But on a year like this does not have 150% fuel moisture in it. It's got about 120% fuel moisture in it. This will burn, right? But it's going to take a lot of heat. There is still water in here. You can all feel it. There's moisture in there. But there's something that we use called the growing season index that helps us understand how much moisture is inside of our living fuels. So the growing season index is something that ranges between 0 and 1. It's just a normalized figure. 0 means the fuel is completely dormant. It's not uptaking any water. As soon as we get to, I don't know, mid-April, late April, that GSI value starts to increase. And then when you get to full turgor, right around normal years, the end of June, early July, you're up to that 300% moisture value. Your GSI is 1, and then it starts to taper down as the grasses or the woody herbaceous material starts to senesce and become decadent again towards the fall. And so we do track all of these things. We do model all of these things. And so those are our live fuels. There is a live fuel component to nearly everything that we see in South Dakota. We can also talk about our dead fuel components. We talk about our dead fuel components in terms of classes, and we class them by size. And so right here in my hand, I have dead grass, again, pulled from behind campus. Hopefully no one wants to light that on fire because it'll burn just fine. But these are what we call our 1-hour fuels. 1-hour fuels. Yes, we classify our fuels by time. And that's a very important thing in the fire world, because when we classify our fuels by time, the smaller time, what we call time lag fuels, are the smaller fuels themselves. So in essence, this is a 1-hour fuel. If it were to be really, really humid out, this fuel would uptake moisture from the atmosphere, and it would become damp and moist, and it wouldn't want to burn. But if the sun were to then come out and it were to become windy, it would only take a couple of hours for this thing to dry out again. Does that make sense? Generally speaking, it takes 4 to 5 time lags for this fuel to come into equilibrium with the environment. And so a 1-hour fuel like this takes about 4 to 5 hours to come into equilibrium with its environment. So let's say this morning, it wasn't, but let's say this morning we had dew on the grass. This would have been saturated out. But then all of a sudden we had a dry line push through, it got really, really dry, the atmosphere was super dry. It would have taken about 5 hours for this grass to dry out. So even though this grass was damp in the morning, by late afternoon it would be available. It would want to burn, all right? And that 4 to 5 time lags is valid for any time lag category. So you take a 10-hour fuel. So a 10-hour fuel is like these sticks, 1/4 inch to about up to an inch. These are 10-hour fuels. These fuels will respond to atmospheric moisture in about 40 to 50 hours. They'll start to come into equilibrium. So let's say today's Tuesday. Let's say it rained last Wednesday, right? These fuels would become wet. They would not be available. But in 4 or 5 days of dry weather, they would sufficiently dry out to become available. Does that make sense? All right, so the fine fuels carry the fire. The 10-hour fuels carry the intensity of the fire, how hot the fire can be. When we start getting up into the larger fuel classes, we can get up into a 100-hour fuel. These are the things that are like 1 to 3 inches thick. So these take 400 to 500 hours to become in equilibrium with their environment. That's about a month, all right? So if we get a big 2-inch, 3-inch rainstorm that lasts a couple of days, really soaks into this, it's going to take about a month for this thing to really dry out, to become available to fully burn. When we talk about 1,000-hour fuels, and Gavin and I weren't strong enough to break off 1,000-hour fuels today, they're like 3 to 8 inches. So, the size of like Hulk Hogan's bicep or something. Big. I don't know why I pulled that out, but I did. But 1,000 hours are the big stuff. right? 1,000 hours are the stuff that can really actually damage the soils. If you have a lot of 1,000-hour fuels and even 100-hour fuels laying on your soils, you can start to bake out your soils. We're going to lose your seed bank in the soils, and you're also going to start to lose the microbial contents within your soils as well. But if you think about a 1,000-hour fuel, that's 4,000 to 5,000 hours that it's going to take to respond to its environment. That's like 4 months. 3 to 4 months. So now we're talking about fuels that are responding to drought scenarios, okay? So your 100-hour fuels, kind of long-term, medium-term dryness, but your 1,000-hour fuels are the ones that are really going to be responding to the overall drought conditions that you're seeing on your landscape. And are we in drought right now in western South Dakota? Absolutely, and so you can imagine that our 1,000-hour fuels are extraordinarily dry. The last kind of thing I want to talk about with respect to fuel moisture is something we call the energy release component. Now this is defined as the amount of heat released from the flaming front of a fire. The amount of heat released from the flaming front of a fire. All right, I'm going to go back a slide, maybe 3 slides. Water is the enemy of fire, and less water, there's more energy released during combustion. All right, water is a really important substance. It contains an absolute pile of heat. So when we talk about energy release component, this actually combines dead fuel moisture and live fuel moisture to give you an idea of how much heat can be released by the fire. If the fuels are really, really wet, a lot of the heat from a fire is going to go into just evaporating water. It's not going to go into burning anything. It's not going to be going into releasing what we call sensible heat, or the heat that you can actually feel. It's going to be going into just evaporating water, which you've all looked at your stove while trying to make mac and cheese. And right, you're trying to boil water, but it takes forever. But the energy release component is another metric that we look at. Oh, by the way, the pictures that I have, top right picture shows some dead woody or fine grass material on the bottom. Those are our 1-hour fuels that are gray, not gray, brown down there. A lot of the times with our ponderosa pine regen, or what some people call jack pine, or just regen, we'll model that as a shrubby fuel. So we'll look at how much live fuel moisture is in it. The picture below that is actually from the Whoop-Up fire in 2011. And if you look at the grass, there's a lot of grass that's available in there, but there's a green component to it, which means that there is a live herbaceous or a live woody herbaceous component to that fuel system down there. And we did have fire go through there. And when that fire went through there, when we're talking about fuel availability, this is what it looked at. The fire consumed all of the fine dead fuels, the 1-hour fuels, the grasses, but it did not consume the herbaceous material, the living stuff that was in there. So that was like the yucca, the snowberry, the other things plant people look at that I'm not aware of. It consumed the grass, but again, it didn't consume kind of the live fuels that are out there. In the fire world, this is what we call a scabby burn. It's scabby. It's burned, but it's not good black. Like, it'll repel fire, but you could still get fire to crawl through there. That's actually what we try to avoid when we're doing burnout operations on fire. We want good, clean black to support our fire suppression efforts. This, on the other hand, this is from the barrel fire. These are 1,000-hour fuels, and so this is up on Elk Mountain. If you go west on Highway 16 all the way to the Wyoming border and just go south, there's an Elk Mountain lookout tower that you actually see from the highway. That whole hillside has burned multiple times over the past 20 years. I think it was the Elk Mountain 2 fire that killed off all those ponderosa pine trees that you see in the background. And then after about 7 years, the tops of the trees fall off, the trees fall over, and then another lightning strike hit, and we had the barrel fire. But this fire consumed these 1,000-hour fuels. And a lot of times when the 1,000-hour fuels are really, really dry, they leave what we call kind of cigar shapes in the ground. It's just this cigar-shaped ash. Or it'll fully consume that 1,000-hour fuel. But then in the foreground, you also see that there's a stump hole there. So the fire is actually working its way down into a dead stump, and then it works its way through the root system of the tree if it's dry enough. And in this particular year, it was dry enough to work through the root system. This year on the Corey fire that we had just east of Custer in mid-March was burning more than that. It was completely consuming everything. Everything was burning. Everything was available. The fine fuels, the heavy fuels, everything was available to fire. Let's talk a little bit about fuel continuity. Fuel continuity just means how tightly together your fuels are compacted. This is the hill behind campus earlier this spring. This is grass that's knee to hip high. Very, very, very continuous. In essence, even without the presence of wind, fire will easily carry through that. And you'll probably get flame lengths on the order of 4 to 8 feet high without wind. Right? But we could flip this over to a different part of campus that looks like this. I mean, it looks continuous from the side view, but if you look from straight down, it's really not continuous. So this would require wind in order to burn, all right? The reason I bring these graphs up, or these figures up, is the prairies of western South Dakota this year in 2026 don't look like that because we have ungulates roaming across everywhere, right? And when the grass isn't growing, the cows are eating everything. So it's counterintuitive, but most of the prairies of western South Dakota look like that. They're not going to readily carry fire. Even though it's a drought year, even though everything's dry, everything's available, they're not going to carry fire because we have animals on the landscape that have eaten everything down to nubs where there's just no fuel continuity anymore. And so, as a fire meteorologist, when I'm trying to assess overall fire potential, that matters. Because if we don't have any fuel on the landscape, we can't burn anything, and we're not going to get really, really big fires. Ironically enough, the Highway 79 fire that was also in March burned about 6,000 acres just south of Fairburn, burnt through what actually was smaller grass than that just fine. It ripped through it. 40-mile-an-hour winds, 50-mile-an-hour winds. But this is also what we use retardant for. So this is a P-3 aircraft dropping retardant again on the whoop-up fire, but that's exactly what we use retardant for. We're breaking up the fuel continuity. By the way, fire retardant is more or less a type of fertilizer, but it just creates a char on the outside of your fuels, and so it doesn't really burn. But it's really expensive, and we've dumped more fire retardant this year than we ever have before in South Dakota, period, and it's only June. Last Thursday, they put 95,000 gallons of retardant out of the Rapid City Airport. At $8.50 a gallon or whatever it is, you're spending a lot of money. That was all for the South Fork fire down in Nebraska. And that was just Rapid City. They were loading DC-10 air tankers out of Colorado Springs that hold 9,000 gallons of retardant. And I think one day, Gavin, you said they had, 9 drops on the fire? So yeah, they've been pushing a lot of retardant in our area this year. We've just been extraordinarily dry. So I got the pre-test for you all, right? We're not going to do quizzes or tests here. We're going to do a pre-test. When do wildfires most commonly occur in South Dakota? Hint, I've put a land use map up, okay? So the east side of the state, pretty much go anywhere east of the Missouri River, you have row crops, right? Soybeans, corn, a lot of wheat too. West of the Missouri River, I grew up in Minnesota. Sometimes it slips out. I grew up on the Mississippi River. But if you go west of the Missouri River, mostly rangeland, but we're starting to get more and more kind of winter wheat, that kind of thing. And of course, the ponderosa pine forest dominated ecosystem that is the Black Hills, along with a few stringers down along the Pine Ridge and Rosebud. So what do you guys think? When do wildfires most commonly occur in South Dakota? Is it March? Who's in March? Tamara's March, all right. Who's July? Who's October? Who's all of the above? Yeah. So it's kind of a loaded question because it really is all of the above. It depends on where you're at in the state. When we look at wildfire occurrence in the state, the east side of the state, this chart right here has months on the bottom, January through December, month 1 through 12. On the left-hand axis is just average acres burned per month. This eastern South Dakota doesn't burn a lot But you can see that the peak is when? March and April, right? It's a spring fire season party for eastern South Dakota. Generally speaking, when they get fires, like this year, actually they had the Tabor recreational fire was like the biggest fire in eastern South Dakota like in the past a long time, down by Yankton. But when they get fires, it's years like this year, warmer than average years, no snowpack, and you think March, all the grass, everything's dry, dead, ready to burn, right? People are still out frolicking across the landscape, and people frolicking, like kids with matches, start a lot of fires. And so, yeah, eastern South Dakota, it's really a March, April time frame. Central South Dakota, now we're talking about the shoulders of the Missouri River. July sees a peak in fire activity, but we also see kind of a fall peak in fire activity. The shoulder seasons in South Dakota, when I say shoulder seasons, I mean spring and fall, are windy times when we can still get really warm temperatures. Fall, we can get a lot of wind, right? The Cottonwood fire that burned in 2016, burned 43,000 acres just east of Wall. It was an October fire, right? We can burn a lot of stuff, right? So that's central South Dakota. But if we go to western South Dakota, guess what it looks like? It peaks in the summertime. But these data are very misleading because I stole it from a project that I worked on back in 2018. By the way, we haven't had a warm season, summer season fire outside of one big fire in the Black Hills since 2016. All of our big fires have been in the fall, winter, or spring. All of them. The only fire that wasn't was a fish fire outside of Sundance that happened 3 years ago, 4 years ago. I was incident meteorologist on that one. But this is where we are now. We're in June. We're going to be looking forward to the rest of June, July, and August, kind of the classic, the quintessential fire season in South Dakota. And so how can we think about what's going to happen over the next 60 to 90 days, right? We do have a sub-peak in March and April. We actually have a sub-peak in November as well. But yeah, mostly a summer fire season. All right, so if I want to create an outlook for our summer, this is what I'm going to look at. I'm going to look at antecedent conditions. What has happened? How much precip have we gotten? How dry it's gotten? How dry the fuels are, etc. Then I'm going to look at current fuels conditions. Because again, if our fuels are too wet to burn, we're not going to burn. But if our fuels are really dry, we are going to burn. Remember, when I'm talking about fuels, I'm talking about 1 hour, 10 hour, 100 hour, 1,000 hour fuels, and I'm also talking about energy release component. And then, on top of that, I'm going to talk about the forecast or the triggers. Like, what is going to be that event that starts the fire, maybe an ignition, or what is going to be that event that's going to push a small ignition to become very, very large? And so, how many of you have ever seen the movie Shrek? Wildfire outlooks are like ogres. We have layers. Okay, so the first layer is the antecedent conditions. If we're not preconditioned to have a big fire, we're not going to have a big fire. The next layer is current fuels conditions. If the fuels are not going to be burned, if they're not going to be receptive to fire, if they're not available, we're not going to have fire. And if we don't have a trigger, we're not going to get a big fire anyways. And so these are the three things that we look at as we constantly migrate through each of the seasons. So back in 2018, I wrote a paper called Contemporary Pyrogeography and Wildfire Climate Relationships in South Dakota. I just really wanted to write pyrogeography in the title of my paper, so I thought it was awesome. Pyrogeography, the geography of fire. And what we found in this study is, and this actually came out of my PhD dissertation as well, is that for western South Dakota, during the month of June, we have to have drought to get big fires. We have to have drought. If we don't have drought, the fuels are too green to burn, they are not available. We have to have short and long-term precipitation deficits. So long-term being, think 3 to 6 months. Short-term deficits, think 2 to 8 weeks. And we also have to have above average temperatures in June. So if we think about this, normally in South Dakota in June, June's our wettest month of the year. It follows our second wettest month of the year of May, right? Things don't really want to burn in June. So if we got to have fire, we got to have long-term drought. We got to have all of the fuel classes that you see in front of you dried out, right? And then we have to have short-term precipitation deficits because we have to stress the living vegetation so that the live herbaceous or woody material is stressed out and it's going to want to burn. And then we want above average temperatures. What above average temperatures do is basically sap out the rest of the moisture. When we start getting hot temperatures, especially combined with low relative humidity, photosynthesis is not happy, right? Anytime a plant goes through photosynthesis, it's got to open its little stoma. And if it's really dry outside, it's releasing a ton of water vapor along with oxygen, right? Well, it's trying to ingest CO2. And so it's that release of water vapor that really starts to dry the plant out, stresses that plant out. July, pretty much the same story as June, but when we get towards August, you start to get away from the drought concept. If we have a really hot summer, we can get big fires in the month of August without having drought or long-term drought. Because in August, we're typically on the decreasing side of the precipitation scale, right? Plants are starting to senesce and starting to dry out to begin with. But let's, for the sake of now, talk about June. What is it, June 16th right now? We still got a couple of weeks left, right? A couple of weeks before the big 4th of July, woo, celebration. Where are we at? Well, in this study, when I quantify drought, I use two metrics. I use the Palmer Modified Drought Index, which is just a drought index. Just think of it as drought. I also use the United States Drought Monitor. So again, two different drought metrics. So if we look at drought right now in western South Dakota, this is what we see. Palmer Drought Index on the left, that's long-term meteorological conditions that are leading to drought. U.S. Drought Monitor on the right. So on the left, those purple colors that you see in southwestern South Dakota are saying extreme drought. -4, which is about as low as you can go on the Palmer Drought Severity Index. Extreme drought. On the right, you see the United States Drought Monitor, southwestern South Dakota, inclusive of Black Hills. We're in D2 to D3 drought, which is moderate drought to severe drought. When we get into D3 severe drought, you're talking about a drought that has about a 3 to 5% chance of occurring on any given year. So if you look over the past 100 years, 3 to 5 years of that should see D3 drought. When we get to D4 drought, like you see in northwestern Colorado and portions of the Nebraska Panhandle, those darker colors, that's like a 1 to 2% chance. So 1 year out of 100 we'll see it. So we're getting down to really the driest years on record. And frankly, since the start of the year, we're bumping the 30s and the mid 50s in terms of drought. So drought's there, check, we got that. So now let's start looking at more kind of moderate, medium to long-term precipitation deficits. This is our year-to-date precipitation, the warm colors being much below average precipitations, percent of average. If there were cool colors on there, that would be above average, but there are no cool colors. If you look at the Black Hills, western South Dakota, it's all in the reds. We're anywhere between 40 and 70% of average across, by and large, western and southern South Dakota. The other part about this that is hiding is the fact that March was January through March was the warmest 3-month period in historical records for southwestern South Dakota. Okay, and that's a database that goes back 1895. It goes back to 1895. The hottest year on record. And it wasn't just for southwestern South Dakota, folks. It was for everywhere in the western United States. It was a terrifying heat wave that we had late winter, early spring this year. So lack of precipitation combined with much above average temperatures. I mean, we hit 90 like 3 times in March. That's crazy. As my kiddo would say, that's cray-cray, right? Yes. All right, let's look at the past 90 days again. So now we're talking more shorter-term precipitation deficits. Once again, you're seeing a lot of the browns and the reds, maybe 30 to 60% average in terms of our overall precipitation over the past 90 days. If we bring it even to the shorter time frame, right, we need a dry June in order to promote big fires. Let's look at the past 2 weeks. It's been extraordinarily dry the past 2 weeks. A couple of stations had a couple of thunderstorms parked over them, which are the purple colors, but it's been fleeting precipitation. And actually, I like to say we're one thunderstorm away from being a desert out here, right? Thunderstorms bring a lot of our precipitation, but they'll get an inch there, inch and a half there, and we won't get any mile or 2 miles that way. And it's been really dry across western South Dakota, especially in the Black Hills. The last precip event that we really had that was widespread was May 30th, May 31st. And then last Saturday, the Northern Hills picked up 1/4 to 4/10 of an inch of rain. Outside of that, there really hasn't been much in terms of precipitation. By the way, this time of the year, we should pick up about an inch of rain a week in Rapid City. If we're not picking up an inch of rain a week, we're not hitting average. We're below average. We're below average, right? We haven't been hitting that metric. All right, so departure from normal temperature over the past 2 weeks. Again, remember when it comes back to figuring out if fires can get big in June, what do we look for? Drought, long-term precipitation deficits, short-term precipitation deficits, and warmer than average temperatures. Over the past 2 weeks, we've seen temperatures on the order of 2 to 4 to 5 degrees above average. All of the layers of the angry ogre are coming in to pointing the same direction, whereas we have the antecedent conditions. That's a green check. We're ready. We are ready to burn, okay? So now when I see that we're ready to burn, I got to look at current fuels conditions. And then once I look at current fuel conditions, I'm going to look at a forecast and be a meteorologist. So let's look at current fuels conditions. Busy charts, but I'll walk you through them. Top chart, bottom left is January 1st, moving all the way to the right through December 31st for both charts. Follow me, top and bottom? Okay, the top chart is our 1,000-hour fuel moisture. So again, this is given in percent. So on the left-hand side of the graph, we have fuel moisture in percent. Higher fuel moisture means wetter fuels. Lower fuel moisture means drier fuels, okay? So let's just talk about the top graph for a second. The blue line, this is a period of record that extends from 2005 to 2024, so about 20 years. The blue line represents the maximum 1,000-hour fuel moisture for any given day throughout the year. So that's like the wettest the 1,000-hour fuels have ever been. By the way, when our 1,000-hour fuels are above 20%, they're just not going to burn, right? There's too much water in there. The green line is the average for that 20-year period of record, and the red line is the record minimum for the time of the year. Black line is this year. Can you see how the black line and the red line are like playing tag? We've been at, or at least very near, record dry 1,000-hour fuel moisture since the start of the year. This is why we've had such an impressive fire year already. But if you look at where we're at right now, is right there. We are very near record low 1,000-hour fuel moisture. And that dotted line represents the next 7 days. Well, actually, I think it's the next 5 days. But it's showing that we're going to actually get into record time of the year dry 1,000-hour fuels. So this is telling me that, yes, we are in drought, but the fuels are showing it. The fuels are so dry where they are going to burn. So now the bottom chart is very similar to the top chart, but now we're showing energy release component. The higher the value implies the more energy that can be released by the flaming front of the fire. So the higher the value is in essence saying that the live fuels and the dead fuels are drier, so when we start them on fire, they're going to release a lot more energy. Once again, I want to point out how many times we've been so the red line now is the period maximum, which means dry. And how many times this year we've been above the record time of year max. We've had a few precipitation events. And by the way, this is for wind cave. I'm not cherry picking data. This is pretty much the same for everywhere across southwestern South Dakota. I just didn't want to show you 1,000 graphs. I mean, I do want to show you 1,000 graphs, but I don't think you want to see 1,000 graphs. So yeah, this is for wind cave, Elk Mountain. That Elk Mountain, different Elk Mountain than I was talking about before. So yeah, our ERCs are going to be approaching or at record highs in the next couple of days, and then actually Saturday, Sunday, it looks like we're going to have a little precipitation event come through, and that's why you see that dotted line drop off back to average. So, check. We're good with current fuels conditions. What about forecast or the triggers? How many of you know what tomorrow's going to bring? Yay! All right, so this is tomorrow's forecast. This is from the high resolution rapid refresh of weather model that we look at. This is peak wind gusts for tomorrow at 3 p.m. our time, 4 p.m. Central Time, showing gusts across pretty much all of South Dakota, anywhere from 25 to 45 miles per hour. Just a snapshot in time. Our wind gusts tomorrow are actually going to pick up in Rapid City about 0800, 0900, so tomorrow morning. And they're going to last through about 2100, 2200 hours tomorrow night, so that's 9 or 10 p.m. This is going to be a 12-hour wind event in which we're going to see wind gusts in the Black Hills and surrounding prairies on the order of 30 to 50 miles an hour. Ouch. That to me is a trigger, all right? When we start approaching 50 plus miles per hour, that's when power lines come into play. When we start approaching those types of winds, any kind of ignition source is going to be extraordinarily conducive to large fire growth when given the antecedent conditions and the current fuels conditions. On top of that, down here on the bottom right chart, is our relative humidity. By the way, these little barbs are showing a northwest wind, so it's going to be a northwest wind tomorrow, which is a very common wind for us. But the colors are showing relative humidity. Anything that is sub-green or not green is less than 40%. Anything that's down in the darker brown colors are in that 20 to 30% range. Tomorrow is a day that scares me because how many of you have heard of a red flag warning? Okay, it's a fire weather warning, right? A red flag warning for western South Dakota. The quintessential conditions are a relative humidity less than 15%, conducive fuels and winds gusting in excess of 25 miles an hour. But that 15% RH criteria, when our fuels are as cured as they are, it's more like 25 or 30%. Every big fire that I've worked on in the Black Hills in the summer months, if we get below 30%, we're going to burn. And this is showing pretty much everywhere across Oglala, Lakota, Fall River, Custer, Pennington County, below 25% relative humidity. So tomorrow, I'm not sure, I don't work for the Weather Service, I don't know if they're going to issue a red flag warning or not. Tomorrow's a sleeper day, right? It's that wind speed, it's those wind gusts that I think are going to kick our butts tomorrow if we have an ignition. So it's all three of those things. So we are completely layered up, right? The ogre is happy. So that's for June. What's July and August going to bring? Well, I know, everyone laughs because I always bring doom and gloom, but happy weather to a meteorologist is really boring. All right, but I do have some positive news. This is a map of a precipitation forecast for the next 7 days. If you look at this map, everything in the green is like 1/10 of an inch to 1/4 of an inch up to 1/2 inch of precip. Everything in blue is 3/4 of an inch up to 1.5 inches of precip. And so this is from my friends at the Weather Prediction Center, which is a branch of the National Weather Service. By and large, we're thinking wide swaths of South Dakota, and this is really a Saturday, Sunday event this weekend, should see, golly, 1/2 inch to 1.5 inches of moisture. Do remember that every week we should pick up 1 inch of moisture. So this is basically saying that over the next 7 days it's going to be average, right? To overcome the drought that we're in, we need to have above average. This is going to be average, but I'm saying that if we can get through tomorrow and get through Thursday without any big fires, Friday the wind's going to back off, Saturday, Sunday, even into Monday, things should subdue a little bit. At least we're going to get some short-term reprieve. This time of the year, in the summertime, if we pick up even 1/4 inch to 1/2 inch of moisture, so let's say we were to get 1/2 inch of moisture today, that puts us out a week. I'm not thinking fire activity for another week. You follow me? So every time we can pick up 1/2 inch, we're not going to have fires. So even though we're in a really dry year, and fuels conditions are good, even if we get below average precip, if we can pick up like 3/10 of an inch of precip a week, I think we're going to be out of it. I think we will. But if we don't, if we're like sitting in Rapid City right now and we haven't seen rain in 16 days and we get a trigger day like tomorrow, we could get a lot of fire activity. So yeah, looking out towards July and August, well, let's venture out to look at that. I'm going to look at the North American Multi-Model Ensemble. It's a glorious name for a model that we run. Basically, it's a model that just looks at, hey, in bulk, what are the conditions going to look like in July or August or September? So this is July. This is a precipitation metric on the left. This is a temperature metric on the right. By and large, the NMME, the North American Multi-Model Ensemble, is showing high probability of below average precipitation for July for our area. At the same time, it's showing high probability for above average temperatures for July for the same time. And because we're only 2 weeks from July, I've given the green check to the antecedent conditions because remember July, we still got to think about drought, long-term, short-term precipitation deficits, and warmer than average conditions. The antecedent conditions are there. Whether or not we get the current fuel conditions or those trigger days is a different story. I might be a meteorologist, but I am not a soothsayer, I am not a clairvoyant, I am not a fortune teller, I don't read tarot cards. I don't know what 2 or 3 weeks is going to bring, but I do know in bulk what we're likely to see across the northern Great Plains, and it is warmer than average and drier than average conditions. Looking at August, I put a question mark by the antecedent conditions because I don't know what July is going to bring yet, because again, I'm not a clairvoyant, a soothsayer, a fortune teller, or a tarot card reader. But July is looking much warmer than average. By the way, with things, decadal trends showing warmer than average conditions and an increasing warming environment, my prediction of warmer than average conditions in August isn't really groundbreaking, right? It's just like, okay, this is where we're at. But this is interesting to me. August, look over the Four Corners region up into western Wyoming. This is showing hints at above average precipitation for that area. Has anybody heard of the desert southwest monsoon? Okay, so what happens with the desert southwest monsoon is the desert southwest heats up a lot in May and June. It becomes really, really hot. Hot air rises, which means air has to come in to replace that air. That air comes from the Gulf of Mexico, the Gulf of America, the Gulf of California, the Pacific Ocean, sorry, oops. And that air converges into the Four Corners region and it creates the desert southwest monsoon. So they get a lot of thunderstorm activity. When the desert southwest gets a lot of thunderstorm activity, what happens is those thunderstorms advect or move moisture into higher levels of the atmosphere. And then, because we have westerlies in this part of the United States, those westerlies take that moisture to above South Dakota. But that moisture exists at 15 to 25,000 feet above the surface. We get what we call high-base thunderstorms. High-base thunderstorms are those storms that you see off in the distance that you can see the Virga shower underneath it, but then the rain evaporates before it hits the ground, and then you watch lightning bolts come out the side of the storm. So we get more dry thunderstorms when we have an enhanced desert southwest monsoon. That scares me. Yeah, good for them. Go Colorado River Basin. But for us here in South Dakota, this screams dry lightning to me and a whole new ignition source. So am I worried about our summer fire conditions? I am. But I can't make any guarantees. We're just looking at our current conditions, what we've seen in the past, and trying to project that forward. Some eerie similarities. All right, so again, a busy graph. But like the other ones, bottom left is January 1st, extending to the bottom right, December 31st. Now this is precipitation accumulation at the National Weather Service office here in downtown Rapid City, right behind campus. The brown line at the top represents average precipitation since the start of the year, accumulated precipitation all the way through the end of the year. So on average, downtown Rapid City gets about 20 inches of precipitation a year. The airport, on the other hand, gets about 17.5 inches of precipitation a year. We're just a little closer to the Black Hills here, so we get a little bit more rain. We're good with that so far. I've got a lot of different years plotted on here. The year that's in green with the green shading under it is this year. That's where we're at year-to-date precipitation. We've gotten about 5 inches of rain in Rapid City downtown, whereas average is about 11 inches. So that's 40% of average, 45% of average. Okay, we're dry. We're really dry. The other colored lines I have on here are 2012, 2016, 2002, 2007. 4 absolute banner years for big freaking wildfires in western South Dakota during the summer months. 2012, we had Myrtle, we had the Longhorn Complex down in the Rosebud, we had Region 23. 2002, I can't even think of all the fire names. Just big fire years. We're drier than those big fire years. So this really does scare me, all right? So there's eerie similarities, but look at all the black dots. Those are the days we haven't gotten precipitation. We could, I'm not gonna tell you right now that we couldn't see this skate back up. It could still happen, but the probability of that happening is becoming smaller and smaller and smaller as the days go by. All right, so this is our Godzilla El Nino. All right, we have El Nino this year. Oh my gosh, what's El Nino going to do? By the way, El Nino is a warming of the equatorial Pacific Ocean waters in the Central and East Pacific. So the map in the background, ChatGPT is awesome, isn't it? The map in the background is our average sea surface temperatures anomalies over the past month, basically. So this band of red that you see right here is the hallmark of an El Nino. An El Nino is a warming of the central and eastern equatorial waters. So now we're talking, by the way, this is in degrees Celsius. So this is an oceanic water that is 1 to 2 degrees warmer than average. Just off the west coast of South America, we're 2, 3, 4 degrees above average. Subsurface temperatures in this area are anywhere from 4 to 7 degrees Celsius above average right now. And that water is getting closer and closer and closer to the surface. So even though the popular media has been calling this a super El Nino or a Godzilla El Nino, it's the truth. We could see one of the strongest El Ninos on record. So I say that to say this. That doesn't matter to me. It really doesn't. El Nino in the summer months really has no correlation to our weather, okay? So in the summer months, you can look at all the statistics of the super El Ninos, the past 15 years, past 15 strongest El Ninos on record. There's really no correlation to our summertime weather one way or another. It's really a wintertime correlation for us, warmer and drier than average in the winter. But for this summer, I don't necessarily have a lot of confidence that El Nino is going to impact wildfire weather or wildfire outlook at all. But I just wanted to put Godzilla on a slide. So some final thoughts. Once again, I'm just a meteorologist. I don't predict the future. I mean, I do, but I don't. I think about it a lot. We try to recognize patterns that are out there. But at the end of the day, we're just a bunch of nerdy people that sit around and talk about this kind of stuff. 2015, it was the driest year on record, year to date, through like April 10th. I was panicking in 2015. 2015 ended up with 25 inches of rain in Rapid City. It's one of the wettest years on record, okay? So these things can happen, these outliers can happen, but once again, I do want to stress that the signals are pointing to a warmer and drier than average summer as we progress through the ends of the months, or at the end of the summer months. So that's about all I got for you today. Things just to take away. Tomorrow kind of terrifies me. I did inform everybody that listens to me today about our fire weather conditions tomorrow, how we're kind of building up all of the layers. The ogre is angry. He might break free. This weekend, I'm hopeful for some precipitation, but I do know that Saturday is also going to bring lightning. And if we don't get a lot of precipitation with it, we're probably going to have some fire starts this weekend. Hopefully Sunday, we can mitigate that with some cooler temperatures and above average relative humidity, maybe some sprinkles. So with that, cheers to you all. I appreciate you coming and have a great evening. Oh, questions? Yes, sir.
Can you go back to the Godzilla slide?
Absolutely. I put it in here for a reason.
So there are a few areas of cool water, blue, slide.
Yep.
What do we know about them? Is that one's in Alaska or near Alaska?
Okay, so this up here is the Pacific Decadal Oscillation. That's a pretty hallmark sign of the Pacific Decadal Oscillation. You get kind of a warming in the eastern, northern Pacific, and then a cooling off the Bering Sea, Gulf of Alaska. Oh dear, off the top of my head, I can't remember if we call it a cold phase or a warm phase of the Pacific Decadal Oscillation. And this is another thing that I want to point out. El Nino is only one oscillation. There's the Pacific Decadal Oscillation, there's the North Atlantic Oscillation, there's the Arctic Oscillation. Shorter term, there's the Madden-Julian Oscillation. So all of these things are like, if you think about different waves, different sinusoidal patterns, they can either constructively interfere or destructively interfere with each other to globally influence weather patterns. The one I'm most concerned about is right under Godzilla's chin. This right there. This has been a signal that's been there for the past couple of years. And from modeling studies, that's showing a slowing down of the Atlantic meridional oceanic circulation. So what's going on is, because we are warming globally, the Greenland ice cap, which is under Godzilla's head, he's breathing fire, is actually putting more fresh water into the Atlantic Ocean, the North Atlantic. What that fresh water does is, fresh water is more dense than salt water, and so it sinks down and it messes with the North Atlantic circulation. There are some scientists out right now that are kind of ringing the bells of this circulation failing over the next 2 to 10 years. And if that were to happen, that oceanic current is what keeps Great Britain, Northern Europe relatively warm in the wintertime. And if they were not to transport warm water up there, they would have record cold snaps both in the summer and the winter, and that might be devastating for any kind of agricultural economy up there. And so this right here is a bunch of question marks. I don't think it's going to impact us here in South Dakota. It'll probably bring cooler than average conditions to the eastern seaboard. But yeah, some interesting stuff. But I'm glad you pointed that out. But by and large, you see a lot of red and orange on that map. And the ocean 2 years ago was the warmest it had ever been, and we're close to it now. Whew, long-winded. Did that answer your question?
It does. I have another about Nebraska, the South Dakota fire. But prior to that, this winter was the largest wildfire ever in the state of Nebraska.
Yeah. Yeah.
What were those conditions like, and what caused that? Presumably it wasn't lightning.
No, so the question revolves around the big fires in Nebraska. So you had the Morel fire, which was 850,000 acres. I can't even remember, Road 203, 204, whatever it was, up by Halsey. Had the Cottonwood fire, which was another 150,000 acres. This year's heat was unprecedented. Absolutely unprecedented. We're 4.5 to 5 standard deviations away from where we should have been. And that is statistically impossible if you just look at a normal historical climate record. There's a human fingerprint on that warming this winter, a big human fingerprint. Combined with the hot temperatures, we had a lot of wind and we had no snowpack all winter. And so again, those fuels were just baking all winter in the above average conditions, above average temperatures and super windy conditions. I actually don't know what started any of the fires, to be honest with you. Up until the South Fork fire, that was started by lightning. I did watch the storm go through. It threw down about 8 lightning bolts, and South Fork fire took off. Yeah, do you guys know what started the other fires down in Nebraska? Sorry, there's some fire guys down. I have no idea. Not privy to that information. But
What was 4 to 5 standard deviations?
so when we look at statistical curves, right, we have a Gaussian distribution, right? Average is the middle, that's the peak. When you get 1 standard deviation away, 2 standard deviations, 3 standard deviations, 4 standard deviations, there's a 99.99% chance that under normal climatic conditions, that would not happen. It should not happen, but it did.
Well, what are you measuring with those? So is that temperature? Or?
That's temperature, for temperature, yeah. Yep, that's for temperature. Yeah, we had, I can't even describe to you how hot the January, really through April period was this year. It was unbelievable, everywhere. What's that?
Snowbirds hang around?
Yeah, yeah, everywhere from, Texas, New Mexico, Colorado, all the way up to Utah, Wyoming, into southwestern South Dakota, western Nebraska. Everywhere in that area saw their hottest 4-month period on record, which is unbelievable. And, I know there's a lot of folks that are going to say, well, hey, white European settlement has only been in South Dakota since 1874, 76, whenever Custer came through, right? We don't have that long base of a knowledge. But the infrastructure that we have is only that old, right? We have built our lives upon a consistent climate that does not exist anymore. That's the problem. Whether or not you want to debate what's causing it, I don't care. Go ahead and debate it. But we live in a climate system that we did not build America on. Whether that's naval bases in Norfolk, Virginia, or the Black Hills National Forest, the ecosystems that we see on the landscape are not designed for the climate they currently live in. I'm passionate. Great question. Yes, sir.
So when you said, fluffy stuff can start on fire, does that mean sheep can start on fire?
I don't ever want to start a sheep on fire. But I would imagine sheep wool does burn pretty well. No, it doesn't? Is it? Oh. Well, this is true. I've heard about this. Houses like pre-1950 that had wool curtains and wool everything, they didn't burn, and now everything's made of plastic and burns really, really well. Interesting. So there you go. No. Great question. The more you know, right? All right. Is there any questions online? Is there anybody online? Oh, thanks, Mom.
I got one last one for you.
Yeah.
So the wind event that happened in December that tore down a lot of things,
Yeah.
structures, trees, etc. How do you expect that the newly downed fuels are going to affect potential fire this summer?
Well, that's a great question. So our big windstorm that we had December 16th, December 17th, we had 90 to 105 mile an hour winds across all of western South Dakota. I do know from seeing it on the Quarry fire that all the trees that did fall down burned. They burned very, very well, actually, nearly fully consumed, which was weird for a tree that's only been dead for 3 months to do. The next problem is going to be access. If we do have a big fire anywhere, think 385, well, even over into the wilderness area, that area kind of east towards 79, if we get a big fire in there, we're not really going to be able to access it. And we had some of those problems on the Greyhound fire. No, not the Greyhound fire. We did have some of those problems on the Quarry fire that was burning. But yeah, access is going to be a huge issue. I mean, one of the biggest ways we fight fire is dozers out here. We put dozer line in, and if we got big giant trees everywhere that are laying on the ground, we're not going to be able to put dozer line in. It's a human safety issue. Even if we get people to get into the area to put the fire out, if we can't get them out safely, if the fire blows up, we're not going to put them in there to begin with. The other thing, and this is the one that I don't know a lot about because I'm not a tree person or a silviculturist, is a lot of the pictures that I've seen of the ponderosa pine trees that are still standing, they got turned. And I think there's a lot of internal damage to them. When I was driving up, and I've seen this down in Angostura, and then driving up 79 through Custer State Park, there's like this weird rusty hue to a lot of the trees. And I'm wondering if, even though they're still standing, if there was enough internal damage or they're dead. Yeah, it's weird. I don't know. And this is total speculation. And I'm really curious to see what happens. But I think there's a lot of unhealthy standing trees right now, which could be problematic in a month or two. Yeah.
Urban forest land.
Yeah.
Rapid City is a lot of urban forest. There have been a lot of mitigation efforts, and also outside Rapid as you come in, barriers of, especially at Sheridan Lake Road.
Sure.
What's your view of the health, or good or bad, of the urban forest in Rapid and the ability to defend it?
I think Rapid City and the Black Hills National Forest has done a phenomenal job of thinning out the overstory, the canopy, especially on the western fringe of Rapid City. You can actually go into Google Earth and you can see it. It's basically a C shape on the west side of Rapid City where there's been miles upon miles of cutting and thinning and everything else. But just because we're taking trees off the landscape doesn't mean there's no danger. So if you have a dense canopy what ends up is those fine fuels, the grasses that you see down here, those are the ones that carry the fire, right? It's rare for us in the Black Hills to get running crown fire, which means fire like up in the crowns of the trees. It's rare, it's pretty rare. What most of our fires are running, they're grass fires under the canopy of trees that are burning up needle cast, okay? So when we take out trees, we reduce the risk of running crown fire, which is good, but what that also does on the flip side of things is it opens up the canopy, which allows more sunlight to hit the fuels, so it's gonna dry the fuels out, and it allows more wind to come into contact with those fuels. And so with a more open canopy, you can actually get faster spreading surface fires that are running through those grasses and the needle cast on the bottom. So you're almost trading out one threat for another, but we can by far control surface fire a lot better than we can control canopy fire. And I think that's why we were so successful on the fire that was off of Neck Yoke Road back in March as well, because the canopy had been thinned. We weren't getting fire up into the crowns where you can now get spotting and ember flood, all that kind of stuff. We're keeping it on the ground, which is good, but it can move faster. So it's changing one threat for another threat, but I think it's a more tolerable threat. But the root of your question is good or bad. And in my world, there's no good and there's no bad. It's what we as a society have deemed to want. You know, we're at the point where we can control the environment around us. And so if we deem it to be good the way it is, then it's good. It's a great question. One more?
Why is retardant like reddish purple?
We color it so we can see it. That's really what it comes down to. So when the pilots go over, so the question is, why is retardant kind of that reddish color, maroon color? So when you drop it, some of it actually is green. Some people have colored it blue. But when you drop it, you can see where you've actually put it. And so when the next air tanker comes around, they can start where they left off and keep going. If it was like watercolor, we wouldn't be able to see it, so we wouldn't know where to start the new line of retardant. Great question.
How do you color it? How do you make it color?
I hope whatever you put in,
Tony, where's Tony?
whatever you put in is flame retardant, flame resistant.
Yeah, it's basically a phosphorus. Yeah, it's called Phos-Check. I don't know, Google it. That's a great question. I'll look it up, bud. All right. Well, thanks again. I appreciate your time in the evening tonight. It's been fun. Thanks.
So there will not be Steam Cafe next month. We had somebody lined up and they had to cancel, so I was not able to find a replacement, so there will not be Steam Cafe in July. There will be in August, so the third Tuesday in August is, let me look at my calendar here, August 18th. And the presentation will be from Dr. John Keller in our materials and department, and he will be talking about the use of materials from the hill behind campus in various projects that students did during the school year, like clay, that kind of thing. So hope to see you on August 18th right here, 6 p.m. Thank you.